coming from the magnetism community and from the spintronics community. And so I'm thinking about having this talk kind of transition from spintronics and what I'm really interested in into then the scanning NV side, which has been done in collaboration here with Konami. First and foremost, obviously, this work involves lots of wonderful and brilliant people. And so this work really started when, during my time at MIT. So I have Jeff Beach's group to thank for that. We have a lot of X-ray imaging data here in collaboration with the group of Gisela Schütz and then Felix Wittman at the Helmholtz Center and the Max Planck Institute. And then most of the theoretical work has been pioneered really by the so-called queen of antiferromagnets, Helen Gomonnet at Mainz. And then we're working together with Norman Burge at Michigan State, who has also been a very active part of this team. And our samples were grown from PVD products in Massachusetts. And then obviously the entire wonderful team from Konami, who has been working with us to understand our data and also look at our samples, and obviously then also Patrick Valentinsky, here listed as part of Konami, but then obviously from University of Basel. So I think what we've heard today already is a couple of introductions to why spintronics is important, and I guess this is also somewhat the community that we're having here today. And why antiferromagnetic spintronics is important, or interesting at least for many people at the moment. I don't think I need to stress either, because we've had wonderful introductions from Vincent just now. But maybe just one thing that I want to emphasize here again is that because of its robustness to external magnetic fields, it's very interesting for applications, but this also makes it really hard to manipulate any sort of state in an antiferromagnet. And so it really just comes down to now, I guess, a quote from Néel, right, originally, where he stated that antiferromagnets are interesting, but useless. And I would claim that today we have actually come to a point where we understand and have enough tools to look at them and hopefully make them a little bit more useful in technologies. So this really came with the breakthrough of realizing electrical control and detection of the antiferromagnetic order. So first, it was detected in very, very special material systems with special symmetry requirements. But this has now also been realized here in antiferromagnetic heavy metal bilayers, as it was as the motivation came really from the ferromagnet heavy metal bilayer structures, right? Where the spinor-rhetorics are very, very efficient at switching these ferromagnetic layers. And what we have seen now is that even though we see some sort of manipulation of the antiferromagnetic state, we also have a lot of artifacts coming into play, and we really need to be very, very careful to separate different thermal contributions from magnetic contributions from contributions that we're not even quite sure yet what we're looking at here, right? And so the other thing that made antiferromagnets actually even more interesting, for me at least, were the recent reports of topological spin textures, where you're looking at not only manipulating simple domain structure for storing bits in, let's say, different directions of antiferromagnetic order, but now also looking at the possibility of storing information in topologically protected structures and spin textures in these materials. And so I think we can basically start with this motivation of knowing that, or thinking that antiferromagnets are very interesting indeed for technology, and disagreeing here with Néel a little bit, but we really need to understand what the domain structure is about and what the formation mechanisms behind this is. And so this talk really focuses a little bit, firstly, on our model material here, hematite, and looking at the domain structure using, let's say, from the spintronics point of view, more conventional ways, including electrical characterization, but then also X-ray characterization. Let me just quickly try and get a laser pointer. Here we go. Thank you. And then really going into what we see in addition to this and how we can relate these more conventional techniques that we are using in spintronics with the very novel and exciting technique of scanning NV magnetometry. All right, so let me introduce you first to a very interesting material. It's alpha Fe2O3, also called hematite. And this is actually canted antiferromagnet. So as Vincent has also already mentioned, this is actually really nice when it comes to both, I guess, controllability with magnetic field, but then also with having some sort of a small ferromagnetic moment that we can hopefully then later on detect in NV magnetometry. All right, so as we can see here, we have this canting of the sublattice magnetization A and B, which then gives rise to this small ferromagnetic moment, which is perpendicular to our nail vector. And what we also have to note here is that at room temperature, we have an easy plane anisotropy. And within this easy plane, because of the hexagonal structure here, we have 3 easy axes given by the magnetocrystalline anisotropy. And one thing that will be very important, and you'll see a little bit later why, is that it has a very large magnetoelastic constant. And this basically relates now the strain with, or deformation of, for example, the unit cell with then also the orientation of the nail vector. All right, so our samples were grown epitaxially on sapphire substrates. And here you can see an X-ray characterization of our samples, really showing the epitaxial growth and the high quality of the crystallinity of our films. Because of this magnetocrystallinity that depends on the crystal structure, this is actually really important to note that we have high quality films here. And then we can read out the antiferromagnetic state electrically, which has been shown by many groups by now. And so basically what this means is that we're looking at the magnetoresistance. So we're sending a current along one direction, we're measuring the transverse voltage here. And now using a large magnetic field, we can reorient a nail vector within our sample perpendicular to the external magnetic field. And with the large magnetic field, we can now reorient all of them depending on our angle of the magnetic field with respect to now this current direction here. And if we go around a circle with our magnetic field, we can really see this very characteristic sine 2 theta dependence. And if we now reduce the magnitude of the magnetic field, what we see, the magnitude of this or amplitude here decreases, meaning that the magnetic field now isn't strong enough to reorient all of the nail vectors perpendicular. And so this is why the signal really depends on the magnetic field below, let's say around 500 millitesla, and above here we see a saturation behavior where we have more or less all the nail vectors oriented perpendicular to the applied magnetic field. All right, if we now look at this field dependence a little bit more carefully, what we see is actually 2 things, right? So first of all, what we see is we have a very small remnant signal at 0 magnetic field compared to the saturated state. And the second thing we see is we have hysteresis in our system. So the hysteresis we can somewhat understand from having a weak ferromagnetic moment, a small ferromagnetic moment. And so this is something that is commonly observed also in ferromagnets. However, the small remnant signal here, we have to think a little bit more carefully about, right? So to understand this and to understand why we have a small remnant signal here at 0, we now went and looked at both electrical, but then also X-ray absorption experiments to really see and visualize what is happening on the magnetic scale here. All right, so the technique that I want to introduce now is X-ray imaging of antiferromagnetic order. And what we've used for this is we use linearly polarized X-rays, and then look at the absorption of those depending on now the relative orientation of the linear polarization and the nail vector. We get bright contrast or dark contrast. So basically, this now gives us an image of our antiferromagnetic order in our system. So now we can look at, well, what actually happens? Why does this electrical signal depend so much on the magnetic field that we apply? So as we've said, we would presume at higher magnetic fields, we orient nearly all of the Néel vectors perpendicular to the magnetic field. And what we see is, indeed, we see very uniform grayish background color here, meaning that all of the Néel vectors should be pointing along one direction, which gives rise to this gray contrast in our X-ray image. When we now reduce the magnetic field to 0, what we see is actually we have a lot of structure and texture in our image now, meaning that while reducing the magnetic field, we actually have formation of antiferromagnetic domains. And these now domains oriented along many different directions give rise to an averaging effect. And this gives rise to this very, very small Remanent signal here. So now what we can say from these X-ray images is that we know, in agreement with our electrical measurements, that we have a formation of a multi-domain state at 0 field. And we can also see how this now reorients again back perpendicular to the magnetic field as we increase the magnetic field. And if you think about these formation mechanisms in ferromagnets, it's very intuitive why we would get formation of domains in the first time, right? Because we have stray fields. But as we've just noticed is that, well, in antiferromagnets, we don't really have these stray fields. And so why do domains actually form in the first place? What is driving this formation of this? And what we actually notice is that instead of having these demagnetizing fields as we have in ferromagnets, what we have in antiferromagnets is something called destressing fields. And these destressing fields are somewhat the analogon of demagnetizing fields for antiferromagnets now. And they're really based on long-range interactions of the elastic subsystem now. And this is, again, now we're coming back to this image here, right? Where we have this coupling of the magnetoelastic system, right? So we have the antiferromagnetic order coupled now also to the strain, which obviously wants to have equal distribution as possible, as much as possible, right? And so this is why we really break up into smaller domains as we now remove the magnetic field, because we want to satisfy both the magnetic contribution, but then also the strain contribution here. And with this, we can really now understand why we have this reduction from our saturated state to our 0 state. But if we now look at the different directionalities, we can also get a little bit more insight into the anisotropy in our system. And what we see is that if we now reduce this saturated state to the Remanent state as a function of the angle of the magnetic field, is we see this, again, a smaller sine 2 theta dependence, but we don't really see any characteristic points here around these 6 anisotropy points, right? And so this actually was rather puzzling to us, because we should be seeing some sort of signature, some sort of preferential alignment along these anisotropy axes, if the anisotropy actually was playing a crucial role here. So we're thinking, well, maybe we actually need something else apart from this magnetocrystalline anisotropy that's driving now this relaxation, right? And so this is where we really now went back into the theory and had a look at what actually makes our system so special, right? We have very, very strong substrate clamping now in our system, where we see that basically, if we want to look at the relaxation as a function of our magnetocrystalline symmetry, we would see that our experimental data here of this relaxation actually does not agree with the theoretical calculation. And only if we now think of an isotropic distribution of different anisotropies, we can see this agreement here of the sine 2 theta dependency in our magnetic data. And from this, we can extract a distressing field which we see is much larger in magnitude compared to this anisotropy. And hence what we see is we have some sort of an effective strain-induced or elastic, long-range elastic interaction-induced anisotropy coming into play. And this is maybe just a little bit more on what we can understand from this here is that, well, while we would want to have basically an equiprobable distribution across our entire sample, very locally, if we now have a disproportion of two different domains around our center domain, this, because it's not perfectly compensated now anymore, will change the anisotropy axis slightly. And this now leads to a small effective local anisotropy, even though we have a global equiprobable distribution of different orientations of domains in our system now. And so now, again, we want to see these things, right? And this is why we went back to, at this point, XMLD imaging, and we were looking at basically this domain structure here. And by doing angle-dependent X-ray imaging, what we can actually do is we can create a vector map of different orientations of the nail vector. And so every color here corresponds to a different orientation of the nail vector, right? And what we see now is that we see somewhat of a uniaxial anisotropy. This is exactly what we would expect from our model, where we see some sort of a local uniaxial or some sort of local effective anisotropy. But on a global scale, we need to then have something more equiprobable distributed. All right. So now coming to the exciting scanning and NV magnetometry bit. As has also already been mentioned before, going to a synchrotron is something that requires a lot of work and is also very difficult to plan and also integrate with all of the different techniques that we're interested in, mostly with magnetic fields and then also electrical manipulation and so on. And so this is why we were really excited to now learn about the scanning NV magnetometry bits. And so thinking about what we would expect from scanning NV magnetometry, looking at the same sample now again, we would expect to see some smaller domains, right? Well, what we actually see is this image here. And when I say we, is this sample has been measured by Kiyonami, and this has been very exciting work that we have been doing together. So we notice two things. So we see here an optical image of our sample, and here we have a little bit of a pad that we also can see here in this region that we're scanning, right? So what we notice in this image is that we have two periodic lines, two features. First of all, we have periodic lines, and then we have some textures underneath these lines, right? And so now thinking back to the X-ray images that we were looking at, where we had smaller but not parallel-oriented domains, this is actually something that struck us as a little bit surprising. And we weren't quite sure what we were looking at here first. And so we basically went back and thought about, well, what else can we do on the sample with the setup that Kiyonami has to put together, right? And so, well, how about we make use of the very fine AFM capabilities? And so we went into this and started looking at, well, let's first have a look at the height or the topography of our sample. And what we actually notice is that we also have periodic modulation of the height here. And now you have to do a little bit of mental gymnastics to basically align this picture here with the previous orientation of the NV image beforehand. And if you do this, you actually notice that these periodic modulations in height actually correspond to now or agree with the periodic modulation also in the scanning NV magnetometry data, right? And so this is actually something that we were then starting to think of. It maybe is a little bit of a crazy idea, but I'll just put it out there and see what you and many of the experts here in the audience say about this. And so we were starting to think about, well, hematite is actually a layered material, right? So we have different layers of these hexagons, and these actually give rise to now the different orientations of the magnetization, right? And so what we also know is that if you, for example, have a slight miscut in the sapphire substrate, formation of these terraces is actually quite well known and studied and has been reported by many people by now. And so what if we thought that we had these terraces formed in our hematite layers as well? And so basically by having terraces now, or steps, we would then have a stray field coming from not only from the antiferromagnetic texture, but then also mainly actually from these steps in between those, right? And so now with this idea in mind, we'll go back to this image now again and have a look. So if we now look at these lines again, we would say, well, all of these parallel lines to each other basically correspond to somewhat of of these terraces, right? And if we now presume that this is true, we can just follow maybe along one line. We will see that we first have some red contrast, and then we have some blue contrast. So we're going from positive to negative magnetic fields here, right? And so basically, if you think again about your model here, is that these lines, while these lines do not necessarily correspond to our antiferromagnetic domain structure underneath, what actually corresponds to this is the difference here along these lines. So we could basically then propose that what we actually see as antiferromagnetic domains is maybe here, this region where these parallel lines are starting with this red here, and then this region here where we have this line in the middle being the blue line, and again here, for example, having a new antiferromagnetic domain. So basically having a couple of different domains here around, and then giving rise to different signatures, again, of these stray fields at these edges, depending, again, on your orientation of the different magnetizations, sublattice magnetizations in a given layer. And so this brings me to the conclusion of this talk already. Basically, what we've seen is from our electrical and X-ray imaging and also theoretical work, we have seen that substrate clamping plays a significant role, and we have both experimental but then also theoretical understanding of what the driving mechanisms now are for the formation of smaller domains in hematite, and have basically figured out that substrate clamping plays a major role in these, right? But also what we've seen now on top of this is that with scanning and beam magnetometry, we see a completely new feature of our samples. And this is really something that we did not expect, and something that we're very happy that we started looking into, and maybe also something that can be explained by somewhat of a topographical features in our system, giving rise to these stray fields at these steps. But again, this is very much work in progress. And so any thoughts and comments you have, I'm very excited to hear about. Thank you.